So first of all, thanks for joining my session, Empower Keyword Search by Text Expansion and Open Search. So myself, Praveen Mohan Prasad, I'm working as an analytics specialist with AWS. So in one of the recent survey reports, uh, 76% of customers reported that an unsuccessful search resulted in search abandonment. And there was another surprising fact that retailers are losing about more than 300 billion annually because of poor search relevance. So this shows that there is a big gap in the search relevance, and there are a lot of machine learning techniques being researched and actively deployed in search retrieval. One such technique is called semantic search. So, what is semantic search? It's all about don't just search by keyword matching, but also search by context and intention. Just have a look at this query, which is coming from the user asking about what is the body of water between England and Ireland. The traditional keyword search throws a result which with the document titled British Cycling. This is basically because there is a lot of vocabulary matching. There's a overlapping between the query and the document, so, the terms such as England, Ireland, and body. But this is basically a poor relevant result, right? Whereas the look at the next semantic search result, which talks about Irishy. So here, this is what the relevant result that we are looking for, and the semantic search was able to understand the query intention and was able to bring back the right result. So semantic search is all about improving relevance by understanding the user's query, not by just overlapping the keywords between the query and document. Okay, so we understand it's all we can do semantic search to improve relevance and do the matching by context. Everybody is interested to implement semantic search in their existing keyword search systems, right? And there is a big curiosity to implement such semantic search systems. So along with all the search engineers, we have our imaginary search engineer called Mike, who is also interested to implement semantic search system in his existing keyword search system. So he asked opinions from his team members how to implement semantic search. Wow, everyone is answering vector search. Okay, is it vector search all about semantic search? Let's explore, is vector search the only option for semantic search? Along with Mike. First of all, information retrieval, any engines that's gonna retrieve a document or retrieve any object based upon the query uh, will be categorized in either sparse or dense retriever. So this is basically categorized based upon how the documents or your objects are stored in the document store. The first one, the sparse retrieval, it's all about the keyword search mechanism. To quickly go into the internals, first, as you see here, first vocabulary is built, which has all the unique tokens across all the documents, and then a score is given for every token against every other document in your document store. So as you see here, this way of scoring will result in a lot of zero values for every document, right? This is basically because you can't expect every document to have all the tokens present in the vocabulary. So this makes the list of scores sparse, which means you have less non-zero values for every document. That's why it's called a sparse retrieval mechanism. And the scores which are non-zero are actually computed by two algorithms called term frequency inverse document frequency or BM25, also known as best match 25. So we are not going to talk about the internals of how these algorithms are calculating the score, but in general, you can just think about these scores are nothing but the frequency scores which are calculated for every token in terms of how frequent that token is occurring in a document in relative to the frequency of the occurrence of the same token in other documents. It's all about relative frequency of token in every document. The next one, the dense retrieval method. Uh, vector search is a dense retriever. So here, this is completely different from the sparse retrieval method. Here, first, a machine learning model is used where a high dimensional embedding space is learned. The embedding space I mean is that here this embedding space knows the semantics of how to place the objects in this high dimensional space. That's how the machine learning model is trained in such a way that it knows to put the similar objects closer in the space, whereas the irrelevant or the objects which are not related to each other will be far away from each other. So in information retrieval world, you can just simply understand this as a relevant document. A query and a relevant document will be closer to each other, whereas the irrelevant document for a query will be away from each other. And this is called as dense retrieval basically because here there are no zero values for your particular document or a query, because it's going to denote a particular point in this high dimensional space, which means it's going to have no zero values and densely packed floating point numbers as a score. So having talked about the basics of on a very high level, we just covered of how sparse retrieval and the dense retrieval is working. So now let's understand the strengths of both the retrievers in terms of what works good compared to each other. First, keyword search is the best for exact matching. So consider a scenario where you want to match for a query which comes with a user ID or a particular document ID or even a user's phone number. Why do you need semantic search there? You can just simply do a keyword search. That's what is expected, right? So keyword search works best with the exact matching, whereas vector search doesn't do an exact matching. The next advantage that keyword search has compared to vector search is interpretability. Pay close attention on this particular aspect because this is going to be the primary difference. Interpretability is where you understand why particular documents have been retrieved for a query. Your sparse retriever by keyword search will be able to explain why such a document was brought up as a relevant document for a query. You have this explain API in OpenSearch, which is going to explain everything, why the score was calculated and what is the overlapping token between a document and query. Whereas in vector search, that's not possible, right? Because it's all about two objects sitting closer into a high dimensional space. You'll just know a score, what is the similarity score between the two documents, between the query and the document, but you have no understanding on why it is a match. And another important factor on keyword search that makes keyword search better is it doesn't need fine tuning. It generally does very well. Basically, we understood that keyword search works on frequency of tokens, right? And overlapping of tokens between the vocabulary of document and query. So there is no need of fine tuning. It's going to generalize well based upon this frequency statistic. But whereas vector search is the other way around. We need fine tuning because vector search doesn't understand your domain terminology because it will be trained with some other general data corpus available outside. And keyword search is going to require less compute and memory and still provide a faster retrieval compared to vector search. So what's there in the vector search then? So we just covered an example. What is making vector search a semantic search, right? So because it understands the context, which is what keyword search is lagging. And this comes closer with the another advantage is that natural language understanding that vector search can do. You can just ask questions in a natural language way, like how do you make conversations, and still and still vector search will be able to understand that as a whole and brings you the documents, which is not possible so easily in keyword search. One another advantage is multimodality, which means vector search can handle multiple model objects. You can put text, images, or audio, video, anything into your vector database, and then you still can do this searching. Okay, so I just put a table and then told you what are the strengths and everything. There was even a research happening to compare this dense retrieval and sparse retrieval on 18 different datasets. This research is called BEER, and the expansion is benchmarking information retrieval on 18 different datasets. Basically, what this research the authors did is that they took 18 datasets from different domains. Different domains meaning like one dataset will be talking about medical aspects. The other dataset will be talking about financial data, and some other dataset will be talking about technology questions and answers. So it's completely different domains, different terminologies, different datasets. The idea was that the authors want to understand which retriever, the dense or the sparse retrieval, the keyword search or the vector search, which one generalizes well without fine tuning on these different data sets. That was the overall analysis. And the result was quite surprising. Vector search poorly generalized on out of domain data. So, whenever vector search was done on the data sets on which the model was not fine tuned, then the vector search performed really bad. And the conclusion was that keyword search was considered to be a strong baseline and was performing better than vector search on an out of domain condition. Okay, so it's all we have just filtered down from vector search, all semantic search only by vector search to semantic search by vector search with fine tuning. That's the important condition here. So now let's see what fine tuning takes to fine tune your vector search and still make a good performance. So fine tuning a vector search model on a high level, first you need a synthetic corpus, right? Because you need a machine learning model for to provide vectors for your documents and queries, which means you need to train that model based upon your domain data. For that, your search logs will not be sufficient. So with the help of your search logs that you have been storing as queries and responses from your web UI, you have to use those samples as few shot learning, and using a large language model, you should generate large samples of query and responses. So this is one of the benchmark that OpenSearch, the service team, has done generating the synthetic corpus. For example, for 1 million documents where they generated 16 queries per document, it took 48 hours using a P3.16x large GPU instance. So once the synthetic data is ready, you have to train a vector model. So this is more like a transformer neural network. It's like, let's not go too deep into that. So simply understand this as a neural network used to train your embedding model, your vector model, to produce that quality embeddings. So here all the synthetic data that you have been generating as query and responses will be the inputs, and the embedding space is learned by the model. So this is where there is another condition that you need some data science expertise here, right? So in addition to the cost incurred for generating the data, synthetic data, you also need machine learning or data science team to do this. Okay, it doesn't stop there. So you have your vector model, which is providing embeddings and sitting somewhere on a server, providing embeddings for your documents and queries. But what about your model drifting? So once you get new documents, new loads of documents coming into your uh, document store, the model starts drifting, which means you need to retrain the model. And whenever you retrain it, you have to reindex all the document vectors again. You can't just update your document vector fields with your new vectors. You have to completely reindex them. This is a costly operation, right? And this is going to happen every time when you get new documents going into your document store. Well, this is hectic, right? So, right from the cost aspect, the machine learning expertise, and also doing it in a cycle basis, it's going to be quite hectic and stressful for a search team, right? Okay, so now Mike, along with us, are wondering, so why not we use the existing keyword search itself to do semantic search? Is it possible? So that's the way Mike is gonna explore along with us. So first of all, to make keyword search work as a semantic search, we should see what's missing in the keyword search. So these are the two things that keyword search suffers from, and this is the same thing that we covered in the initial comparison of keyword search versus vector search. One is vocabulary mismatch, and the keyword search like not capable to understand the context. Let's understand these two things with an example. Consider you have a document which tells like exercising regularly makes body and mind stronger and healthy. This is a document sitting in your document store. And there is a query coming in asking the user is asking how to strengthen the physical and mental wellness. Okay, so if you see here, there is no common items, common tokens or keywords between the query and document, right? And as a result, the keywords are just going to tell that even though you have this document in a document store, it's not going to be brought as a response because there is no keyword match. There are no common token match. But actually, we have good similarity between the document and query, right? We have the document as body and the query has physical and mind mapping to mental, stronger to strengthen, healthy to wellness. So we have good similarity basically, but because of this vocabulary mismatch, meaning there is no exact matching between the vocabulary and the incoming query and the non-contextual understanding, keyword search is not able to provide this document as a response, which is the actual relevant response. Let's see how we can fix this. Okay, so in the formula of a keyword search, to make it a semantic search, what's missing? What's the factor missing here? Text expansion. So when we are able to expand the documents and optionally queries and then do your keyword search, we can make it a semantic search. So when I talk about expansion, what I mean here is three different aspects of expanding your documents and queries. One is rewriting, which means you're rewriting your existing keywords in its very different format. Number two is injecting contextually similar new words. Number three is compression. Compression meaning just throw away the less important words and just focus on the important words in your document. Let's cover this with an example. So consider the same document. Exercising regularly makes body and mind stronger. Okay, so how can exercising be rewritten? So maybe exercises could be rewritten format of exercising. And what would be the new words, injecting new words here? Maybe workout, training, activity, and gym could be possible contextually similar words that can be injected. So likewise, if you are able to rewrite and inject the complete document term by term or by the by document in total, then we can achieve this text expansion added to keyword search and make it work like a semantic search. We will cover about compression in the further slides, but basically we are trying to uh, talk about rewriting and injecting your documents and queries. Okay, so how do we do this? First thing, the simple way that we have straightforward in open search is you do your custom rules, you understand your data, you know your rules, which is going to be similar, and then you start writing them. You just start writing them in a file, something like, okay, A is equal to B, and this is the expansion of this particular abbreviation, and you just write this in a file. Keep writing using rules. You keep writing a file, and then you upload it into open search. And then open search understands that, okay, this is the conditions that we have to understand in terms of considering them as same tokens, and then it does matching. But there is a pain point here, right? We have to manually write all the rules, understand your synonyms, everything, and it's a pain point. So what's the next way? Like, how about using machine learning for expansion? So basically, this is an area which has some research works till now, and the most popular models that does expansion of your text documents and queries is sparse expansion using Splade. Number one. Number two is doc to query. We will cover how these models work, but generally these are the popular ones that had been working better in terms of expanding your documents and queries. Okay, so document expansion by query prediction, doc to query. So basically, what we are trying to do here is take your document, feed it to the model, doc to query. It's a machine learning model, sequence to sequence transformer, but basically understand that as a function. It's going to go into this function, and the output is going to be a set of queries. Okay, it could be 5 or 10 queries, or even a single query. And this query is going to be more relevant to your document. And then you take this query, concatenate with this document, and then ingest into open search index. So once you do this concatenation and indexing into open search, then you do a regular keyword search. Okay, so let's see how this is going to rewrite and inject as per our text expansion technique. Okay, so two important things happen here by Dr. Corey. First thing is rewriting your existing words, which we just covered with an example, doing its different format of the same word. Number two is duplicating. So, what's the importance of duplicating the same word again and again by this Dr. Query? So, consider the same example. Exercising regularly makes body and mind stronger and healthy. So, Dr. Query generates these as questions here. Okay, so there are different questions which is more suitable for the document. And as you see here, first the exercise word is rewritten and also duplicated again and again. And exercise is the most important word here, right? It is the actual subject of the sentence. When it keeps duplicating again and again, that's going to increase the frequency score of a regular keyword search, which means that's going to be an important word agreed by the keyword search sparse retrieval system. And in addition to that, you see like the new words are injected. Quite surprisingly, I was even seeing the word muscles for this sentence, exercising sentence, which is really good, right? Because anything related to muscle is going to match this exercising. Contextually similar. This is what we do in vector search in form of vectors. We are trying to do this in keyword search itself. Okay, so this is how Dr. Curry works. So just a slide to explain how Dr. Curry generalize. Like in the same research, beer, uh, the researchers found that Dr. Curry was outperforming the basic keyword search, like in 11 out of 18 datasets, and providing a competitive performance on the remaining datasets. So another important surprise was that Dr. Curry was outperforming the vector search. Just the basic keyword search expanded with these questions was able to outsmart vector search. Why this makes it clear when we do text expansion, like which is not fine tuned on your questions, you can still achieve reasonable performance to what vector search is doing, or sometimes even greater than that. Okay, so the next way of expanding your documents and queries is term expansion using contextual features. So this is based upon the model called SPLADE. It's sparse lexical expansion model for information retrieval. So basically, coming to our text expansion understanding, it's going to inject contextually similar words. And number two is expanding and compressing less or more important terms in the sentence with weights. We'll go with an example of how this is going to work. Okay, so consider these two documents. Apple products are expensive, and an apple a day keeps doctor away. I just took basic sentences, but with one keyword match Apple, but in a very different context. Okay, so the first one, which talks about the brand, the gadget, the budget, right? They're expensive. When this was put into the SPLADE model, again a SPLADE function, you can think it about as a function. So what happened is like these were the list of terms that were injected as new contextually similar terms, something like expense, chip, iPhone. Also we get Steve Jobs, mapping to Steve Jobs. So in addition to this, we also get the term weights. So these weights are going to tell how important this particular word is to the sentence. Okay, so map this to your frequency score technique. So basically, this is going to tell as boosting parameters, telling this word is very important. So any query coming with this word, or any query coming with, for example, expense, is more related to this particular document. On the other hand, an apple a day keeps doctor away. It's all about a fruit and a health aspect, some kind of medical advice. So as you see here, we have injected new terms with the help of SPLADE model and the relative term weights for those extended terms. Okay, and just an example, we have got daily, prevent, medicine, and happiness. Yeah, this is quite good, right? Because even though the word was same, like how we see in vectors. Now just the basic keywords was able to expand in a very different way based upon the context. Okay, so again, coming back to the research of Splade, like how it generalizes well, like on different data sets. So on the same 18 data sets, like they use 14 out of it to test Splade. So Splade was the winner. So basically, it outperformed BM25, the basic keyword search, also the dense search, dense retrieval search, the vector search. It was able to outperform vector search and the keyword basic keyword search, and it was considered to be the leading in sparse expansion technique. So we don't need vector search alone to perform this. Okay, so how to implement sparse features that we just saw here in OpenSearch. So basically, there is a field type called rank feature or rank features, where you simply give the all the extended terms along with the weights, and this is going to basically understand that the documents to be boosted or decreased, or to boost or decrease the relevance score of the documents based upon the weights you add. So in simple, you'll be just adding the index with this additional field. For example, here, additional metadata is a new field with the type rank features. And what I do is simply take all the outputs from this played model for the document, and then I put it as rank, and then I inject into the rank features field with the weights and the extended terms. A small tweak can be done here. You can just remove the terms which have weights lesser than some threshold. What I did personally is I tried removing the terms which were weighing lesser than 1.0, basically understanding, okay, these are not important for my document. So that's where you're compressing your document with less, throwing away the less important words. Okay, and then for the query coming in, you do the same thing. You expand your query with all this document with all these terms and weights, and you can use a boolean class with should inside the should class, where inside the should class you can have every rank, every term given by the split for the query along with the weight. You can also add the original query string into that should class. This is a way in a compound query you can add multiple rank features that you get from split along with the original query to search in all the fields, trying to enhance keyword search in all possible ways you can. You can just experiment with this fine tuning, which is working better for you. Okay, so one last thing. This is one of the very recent research work happening in May 2023, that was released in May 2023. This is on the query side expansion. Okay, basically they are using large language models to predict the documents, pseudo documents for the query coming in. Okay, for example, there is a query which is going to be a question that could be given to LLM, and pseudo documents can be generated, and then the same concatenation process can work. So again, this is also proved that it works 3 to 15% better than the basic keyword search with this expansion technique on the query side using large language models. But one caveat which is to be considered a lot is latency. We talked about document expansion, everything which is like done offline, batch in a batch phase. But when we do it in the query side, it's going to take some time, right? Because it's going to hit a model, and then a large language model to generate the pseudo documents. That's going to take some time. So the latency is a factor here, where there was a reasonable hit in the latency on this research. So this is one of the caveat in this process, but basically this is another idea of doing it. So this is all that happened that the authors of Beer tried with the data sets with the different search engines there. This is what I tried with OpenSearch. First doing a basic keyword search, and then keyword search with doctor query, keyword search with Splade, and keyword search, I mean, the vector search with Colbert model. So this was the overall result. So these numbers, you can just think about the relevance numbers. So NDCG is a metric that's gonna tell how, I mean, that's gonna calculate the relevance based upon the position of documents for a query. So just think about the relevance numbers. Higher the number, it's going to be the greater relevance result of for the first 10 documents. So NDCG at 10 meaning for the first 10 documents, based upon the positions, the relevance is calculated. So this was the inference more equal to what Beer authors have found. I mean, Beer and the Splade authors have found. Basically, the keyword search with Splade was number one. Keyword search with doctor query was number two. And vector search was number three. And finally, the basic keyword search, right? So vector search was outperformed by two models in my experiment as well. So Mike got his answer along with this, right? So it's not always vector search for your semantic search. Semantic search is not biased for vector search. You can also do keyword search and still achieve semantic search with expansion techniques. I just found this meme so relevant to the research. Keyword search still worthy because expansion is there.